Hello everyone, I'm Mojtaba and welcome to another episode of A Sip of Chemistry. Today's guest is very special to me, my PhD advisor, Professor Scott Kroeker. He began his journey in nuclear magnetic resonance with high-resolution solution NMR during his master's studies. Later, he developed a keen interest in solid-state NMR spectroscopy. However, magnetic resonance isn't his only research passion. He also has done extensive studies on the structure of borate and borosilicate gases. In this episode, I asked him a wide range of questions, such as what's the difference between a material scientist and a chemist when they study glass? And how has the quality of NMR data changed over the past few decades? We also discussed the most recent NMR symposium he chaired at the CSC 2024 conference in Winnipeg. But there is a bonus in this episode. Professor Kroeker is also the vice president of the board of a family business specializing in potato farming. However, this isn't a typical farm. Watch until the end to discover what makes it so unique. He gave a tour of their potato farm and packing facilities. Don't miss it. Well, please stay tuned and enjoy this exciting interview with Professor Scott Kroeker.
Thank you so much, Professor. Thanks for doing this interview. I've been waiting for this moment a long time. It's in a year.
Well, it's my pleasure.
Yeah, thanks. So, who is Scott Kroeker? Please tell us more about yourself.
Oh, Scott Kroeker is a rock guitarist and a photographer who lives in Steinbach. I keep getting confused with him because people see his photography and they say to me, you are a really good photographer. And I usually say, oh, thank you very much. But sometimes I confess that that's not me. That's a different guy. But Scott Kroeker, me, I am a professor of chemistry at the University of Manitoba. And my research program focuses on NMR spectroscopy of materials, solid materials, mostly disordered materials, a lot of glasses. This is where I'm going to hang my hat.
You did your master here in University of Manitoba or Halifax? I'm getting confused. You did your master here in University of Manitoba. You didn't do glass at the time, right? The NMR study of the glasses.
No, I didn't. Well, actually, my magnetic resonance origins are in imaging. Even before I did my master's, my undergraduate research at the University of Winnipeg was done in MRI. So I was looking at rats. I did some fairly unpleasant things to rats and watched their brain signals, both in imaging and spectroscopy, phosphorus spectroscopy, because at that time I was pretty sure I wanted to go into medicine and do medical research, particularly, not maybe as a doctor per se, but as a researcher. And I really enjoyed that. But then I did an undergraduate research award in Halifax. So in my fourth year of undergraduate, I went to Halifax for a summer and I worked with Rod Weselishin, and I just absolutely loved what he was doing. It was a very exciting summer, and I loved the science. I loved the NMR, and I decided to change my direction. But because of the personal aspects, it was not convenient to go directly there. So I spent my first graduate degree of my NSERC graduate degree scholarship with Ted Schaefer here in the University of Manitoba. And Ted Schaefer's focus was on ultra high resolution NMR. So we were looking at J couplings, not 1, 2, 3 bonds, but maybe 7 or even 8 bonds away. So very, very small J couplings. ultra high resolution. So we had to spend a lot of time trying to get the narrowest peaks possible. So we had to shim a lot. In fact, we would stop our experiment during the acquisition and then shim, and then we would resume after 8 scans or 16 scans. We would degas our samples, So there were it was a lot of work to get very narrow peaks, but in the end, we did that. So that's how I spent my master's, physical organic chemistry.
Then you did your PhD in University of Dalhousie.
I did my master's fairly promptly, actually, just because I wanted to kind of get it out of the way. And then I went to Dalhousie to work with Rod. And there I switched my focus quite dramatically from ultra high resolution, very, very narrow peaks to very, very broad peaks. I did solid state NMR, I did quadrupolar NMR, and very often I was doing really, really broad acquisitions, megahertz or more. So it was a complete shift of focus, but it still stayed in the NMR realm. And Rod, in those days, he did a very wide variety of NMR spectroscopy, all in solids, mostly focusing on, well, not mostly, but focusing on unusual nuclei, many of them. And sometimes we joked that we did Aldrich chemistry. So we would take the Aldrich catalog and flip through it and say, oh, that looks like an interesting compound to look at. And so we would buy it and then run it. So we were it was a physical and theoretical group. So we were really focused on how deeply can we go into the NMR interactions in this simple compound. So model compounds, simple compounds, which are meant to be models for other more complex systems. And so we learned a lot about very small systems. And that was how I spent my PhD. We did a lot of computations. We did a lot of optimizing, a lot of interesting experiments. I enjoyed that very much because I really liked focusing on one thing and getting really deeply into it. I was also thinking that maybe it would be nice to try to apply some of these ideas to more broad applications. So something that might be more useful in technology, for example, or materials. And at one point I asked Rod if it would be possible for me to collaborate with Jeff Don, who was at Dalhousie at the time, doing some work on lithium batteries. And there was particularly a glassy material. It was an aluminum, I don't even remember what it was now, aluminum borate, I think, with lithium in it. Probably some phosphate in it. And I said, this would be a really great opportunity to use what I've learned as a PhD student to do something that would be more applied. And Rod said, oh, no, it's too complicated. And he discouraged me from doing that. And so in my postdoc, I decided it was time to start to do some of those complicated things.
Yeah.
And, well, Rod was right. It was too complicated. It's really, really complicated. But yet, through a combination of advances in techniques, advances in instrumentation, and just more knowledge about these systems, it has been possible to get useful information about these types of things. So my postdoc was with Jonathan Stebbins at Stanford. Jonathan is in their Geological and Environmental Sciences department. So I was particularly interested in doing high temperature NMR when I went there, because that was unique. He had a unique setup. As it turns out, I didn't do any high temperature NMR while I was there. The equipment wasn't optimized. There were some other things that were maybe more interesting at the time. But that was where my love of glasses was born, because, of course, in geological sciences, there are a lot of silicate glasses which are of interest for various reasons, as melts and volcanology and various other aspects. So Jonathan's work in glasses really inspired me. Now, Jonathan also worked on some non-geological glasses, and he had quite a lot of interest in material science. So borates and borosilicates, which don't have any obvious geological connection. I mean, there are tangential geological connections, but no obvious direct geological connection. And so a lot of the work that we did was on borates and borosilicates. And that's where I really began to love glasses. Hey. When I started my own research program, I had fallen in love with glass. And so I wanted to do something in that area. But a good friend of mine, Jerry Chan, said, he was a few years ahead of me. He said, "Oh, be careful because glass is very difficult. It takes many years to become a glass scientist." And at this point, I was just an NMR spectroscopist who happened to be interested in glasses. And I said, "Oh, Jerry, come on. I mean, I'm a chemist. I understand how structures are." Well, he was right too. It takes a long time to really settle in and understand the nature of glasses. Of course, the physics is the same, but there are nuances and there is a language and a culture and a way of thinking about amorphous materials and about melts and about dynamics and all of those things in glasses, which is distinct from the crystalline world and requires quite a lot of bedding in, quite a lot of getting used to it.
Yeah, I see. A long journey, right? From your graduate study till now. So, do you know yourself a glass scientist or an NMR spectroscopist?
Oh, wow. Either or questions are passé, don't you know? We don't live in binaries anymore. We're always somewhere in the middle. And I wouldn't want to commit to one of those. I certainly started out thinking of myself as an NMR spectroscopist. I go to a lot of glass conferences. I think I can talk the language. I think I understand what's going on. I feel comfortable there. But I'm not sure if it's necessary to really commit to one or the other.
Yeah.
What I will say, though, is that I no longer take it as my goal to develop new methods for NMR. At one point, I was very interested in new methodology, and I think I could have gone that direction, but in Jonathan's group, the focus was always on applications. How do we take what we already understand from NMR, because there are so many interesting questions that NMR can speak to, and so I would say I'm a person who understands the NMR quite deeply and tries to apply that deep understanding to interesting questions in glass science.
As a chemist, my background is material science and I worked on glass science. I didn't know that in chemistry they work on glasses. So as a chemist, how do you see a glass? And what's the difference in these two perspectives? I mean, a material scientist and a chemist on working on the glasses.
Well, are crystalline materials part of chemistry? I would hope so. We teach solids, liquids, and gases, and we teach about crystal structures. A crystal structure is condensed phase, which has fairly fixed orientations with respect to each other, with respect to other atoms. Glasses are another condensed phase, and glasses have the same type of bonding as crystals. And they tend to be not very different from crystalline materials in many respects. Of course, there are key differences. The key differences being that it's not a thermodynamic minimum, and another key difference being that there is this intrinsic disorder on the long range. I've never considered there to be any kind of awkwardness being a chemist who works on glasses. I think the only real issue is that we typically don't talk about glassy materials in a chemistry undergraduate program. Whereas I think we should, because glasses are very important and we use them all the time, even without knowing that we use them.
Yeah. So I didn't mean that either one should work. I just wanted to see the different perspectives, and there is a difference, to the best of my understanding. Material scientists, they would love to improve the properties. They don't, not always generally, they don't care about the structure. But you mainly care about the structure and how the property, changing the structure, subsequently change changes the property, right? Is that true?
You're putting words in my mouth, but I can't disagree. I think there's a popular perception that material scientists and engineers are more interested in the final product and the final performance of that product than they are in how they got there. And it is certainly true that there are examples of materials which were made by some means, not always specified, not always completely understood, and they work, they do something what they're meant to do. And there's less inquiry into how they work or why they work from a chemical standpoint. I think glasses are one example. Cements and concretes are another example. We use a lot of cement and concrete. We rely on it for many reasons. But actually, the chemical details of setting concrete or cements are poorly understood from a mechanistic standpoint. It's not like we know nothing, but it's another very, very complex system. And to really go into the chemistry and understand all the different components that move around and that have to change in hydration levels, and those are very difficult questions.
Yeah.
A chemist concerns themselves with these types of questions. But a chemist concerns themselves with these questions because they want to understand the final. Now, this might not always have been true, perhaps decades ago or maybe centuries ago, but at least some period of time ago, people would be interested in these factors just for the sake of curiosity.
Yeah.
Curiosity-driven research is not really en vogue these days. And if we want to do curiosity-driven research, we have to cloak it in applications-driven research. So I think that in most chemistry departments now, you will find people who are trying to understand mechanisms and structures and processes in view of the final application. So it's a very teleological or utilitarian approach to science. And of course, we're pressed to justify our research funds in terms of how is this going to benefit people or economy or whatever, or health or environment. I don't think this is a bad thing, but it is a change in how we have how we view science over the past while.
So in glass science, one of your expertise is studying the interaction of water and the surface of the glass. When you do the dissolution study, what are the challenges for studying the glass surface after dissolution, during dissolution?
Well, let's back up a little bit. One of the reasons that we've been interested in this is because of the long-term immobilization of nuclear waste. So nuclear waste disposal is something that I've been orbiting for quite a number of years now. In fact, I think I started thinking about this in my postdoc already and didn't really do anything about it. But once I got here, I started being a bit more focused on what kinds of materials do we need to develop to make sure that the radioactive waste that we're generating for power, for example, will still be immobilized, will still be intact, will still be safely encapsulated, if you want to use different words, 100,000 or 1,000,000 years from now. So chemical durability is really important. And over the course of my career, I have used NMR spectroscopy to look at various aspects of that process. And much of the work that we have done is focused on trying to understand how I'm going to call them problem elements, the elements that aren't easily incorporated into a glass. Remembering that nuclear waste is a very complex mixture. There could be 30 or more different components that are present in the nuclear waste. And we're asking one glass, one composition, one, let's say borosilicate or boroluminosilicate, to include all of those ions forever, effectively. That's what we're asking of our materials. So there are certain elements that don't tend to be incorporated quite as easily. They tend to phase separate.
Yeah.
And for a long time, this was a big question in the industry. How do we prevent this phase separation? And so our first focus was trying to use NMR to distinguish between crystallinity and glassy components in a single piece, single composite. And I think that we've largely solved that. We've been able to do that. And one of the reasons that we've been able to do that, because NMR is really ideally suited to ask questions about complex glasses. I see NMR and glass as kind of hand in glove, because the questions that glass scientists need to know from a structural standpoint are, what is the local environment of this particular element? And that's exactly the question that NMR is capable of answering. And in a complex glass, whether it's aluminum, boron, silicon, phosphorus, molybdenum, whatever, we can ask those questions specifically to those particular elements and then build up a picture which is effectively the only possible picture we can generate for a glass, because we don't have a unit cell, which is translationally periodic. So this use of NMR is particularly valuable for these types of things. Now, many of these problems have been solved. It's been many decades, and we've developed some new glasses, which I think are useful for this purpose of incorporating more elements with a high degree of durability. So we've patented a few of these compositions, and we're interested in learning more about how versatile they are for more, let's say, realistic waste disposal scenarios. But everything we've done so far is about the pristine, intact glass. We make a glass and we study the structure. We've gone so far as to do high temperature NMR because, of course, as radioactive processes occur, heat is given off. So for the first several hundred years, this glassy monolith underground is not going to be at 22 degrees. It's going to be at something like 300 or maybe 400 degrees. So we've also done high temperature NMR so that we can study what are the processes and the species, the identities of the different complexes and interactions at higher temperatures. So we've gone that far. But what happens 1,000 years from now? Perhaps in a deep geological repository, things change over 1,000 years, over geologic time, 10,000 years. Perhaps water gets in. Perhaps it breaches the canisters. Perhaps it interacts with the glass. We need to ask the question, what happens to the glass? And specifically, what happens to the radioactive nuclides, isotopes, when water interferes? And it turns out that, of course, we're not the first to look at this question, but it turns out that in the presence of water, the surface of many types of glasses alters in such a way that it reduces or limits the transport of radioisotopes from the bulk glass into the surrounding liquid. So this surface layer, this altered surface layer, proves to, in many cases, have what looks like a passivating or protective capacity. Well, that's useful information, but it's information that we need to model because we can't wait around for 10,000 years for it to happen. We have to force the issue a little bit. And when we force the issue, we will almost certainly be dealing with a situation where we have a very tiny skin or surface and a lot of bulk. And from an NMR standpoint, from any analytical, not from any analytical method, but from an NMR standpoint, we need to know how can we distinguish the signals that we're getting from the surface that's been altered from the signals that we're getting from the bulk glass, which has not been altered by aqueous dissolution or by some kind of interaction. So the challenge then comes to how can we be surface selective? And there are a number of ways to do that.
For the last question in glass science, I would like to ask about the ICG, International Committee on Glass. You're a member of the ICG. Last time in Prague, you attended. It was live in person. So what were the highlights in that committee?
Yeah, so I'm a member of the what's called TC3, Technical Committee 3, which is focused on structure of glasses and I guess peripherally also structure and properties of glasses. But really, this is a group of people who all come with different angles on glass structure, different analytical or calculational or theoretical approaches to understand the structure of glasses. And it's quite remarkable that when you get 15 experts on glass structure in the room, we don't always necessarily see eye to eye on everything. And so one of the questions that we were asking, probably the main question I would say, is the question of how do we define glass quite definitively, defining definitively. There have been quite a few attempts to define glass, and some of them are short and punchy and incomplete. Some of them are long and wordy and maybe a little unwieldy. And it was interesting to me that in that group of 15 people, we couldn't agree completely on what really defined a glass.
It's interesting, isn't it? After several hundred years.
It's true. It is very interesting. Of course, let's be clear. We agree in the main. We know what a glass is when we see it, as we say. But to articulate it and define it in a very clear and unambiguous way that includes all glasses is tricky, because let's not forget that glasses are not just silica and just aluminosilicates. There are many, many types of glasses. For example, what about non-oxide glasses? What about organic glasses? What about metallic glasses? Once we start to take a broader view, we realize that, all of these ways that we, and I'm speaking for myself as a person who works in oxide glasses, I think about oxide glasses, I think about Zacharias' rules, or I think, well, my goodness, these conceptualizations don't necessarily apply to organic glasses, which are glasses in their own right. So the challenge really comes, I would say, in asking the question, for whom and for what purpose do we want to define what a glass is? Do we have a specific, are we going to say that's a glass and that's not a glass? Or are we going to say, we're only going to define it for the purposes of, is this for teaching? Or is this for, I don't know,
Publish.
Sure, yeah, it's an open question, I think. Sometimes we define things because we feel like we like to nail it down.
Yeah.
Like killing a butterfly and putting a pin through it and say, okay, now we have the butterfly. And of course, sometimes it's better to let the butterfly fly.
Yeah. Interesting. So let's move to NMR spectroscopy. One of the tasks of your students when they joined your research group was to build up their own probe in old times, not nowadays. So what was the idea behind it?
NMR spectroscopy has become a user's tool. It's very easy to go downstairs as a chemist. You make your little stuff and you put it in a tube and you put it in a sample holder and press a button and it will do its job for you. You don't really have to know anything about NMR spectroscopy. You just have to know which buttons to press. Okay. Well, there's value in that. There's also danger in that. And the danger comes from not really understanding what goes into this process by which the data or the spectrum or the numbers or whatever it is you're looking for come out. As a solid-state NMR spectroscopist, I've always been pressed to understand more deeply the physics and that give rise to the interactions that I'm seeing. And I think that's necessary in solid-state NMR because there are more interactions that will affect the observation. It's also necessary for me because I'm not just interested in hydrogen and carbon and phosphorus. I'm interested in nuclei across the periodic table. And sometimes we get into some pretty complicated nuclei. So to understand something like how to roll a coil, how to understand the electronics and the circuits that are associated, because some circuits will be more effective for lower gamma nuclei, others will be more effective for higher gamma or for medium. Some will be better for doing a very wide sweep width, and some are particularly good for narrows. All of these things really should be understood in order to completely understand what it is you're getting out of the spectrometer. And I'm sorry to say that even solid-state NMR has become enough of a black box for many people that you can take your sample, put it in a rotor, spin it up to whatever, get your spectrum out, and not really understand how it happened. So making a probe is a way to ensure that you really understand the electronics and the circuitry and are able to not just troubleshoot and not just maintain and repair, but really get it. Really, some people say grok NMR. That's very true. I'm finding as I read the literature, as I review papers, that there are too many people who are eager to use NMR, which is great, but without the necessary background. And so something really simple like in boron 11 NMR, if you use a 90-degree pulse, you might not get quantitative intensities for your 3 and 4 coordinate boron, but people don't know this because they don't really understand the NMR experiment. So this is a simple thing, but it manifests in misinterpretations in the literature. It propagates because not everybody who's reviewing those papers necessarily understands that either, or maybe they understand it, but maybe they don't pay close attention to it. And so suddenly we have numbers and data in the literature which are actually artifacts of misunderstood or poorly understood NMR parameters.
So I wanted to ask a question about the data in NMR spectroscopy. When I was talking to James Shelby, Professor James Shelby, a glass scientist, he said over the time, the quality of the glass data, it's declined, specifically TG values. So what do you think about the NMR data?
I would say I would have to agree and disagree with him on this with regard to NMR data anyways. It's getting easier and easier to make measurements. So you don't need to be an expert. You don't need to be a specialist. That's a good thing. More accessible, more people can use it. Because people don't necessarily understand the in depth, it's also easier to either misinterpret or to end up with spectra that are not faithful to the structure. So I think the data look better, they look nicer, but appearance, like signal to noise, for example, doesn't necessarily translate into better information. So like many things, the widespread availability of solid-state NMR in glasses is a good thing, but it has to be matched by knowledge and caution and a full understanding of the technique. And if it's just one technique out of many, if one is just a user without really understanding it, it can be misleading.
You have chaired many NMR symposium in different conferences. The last one was in July 2024 in Winnipeg. Did you see any work that impressed you, you liked it a lot? Will you talk about that conference?
Oh, it always impresses me. I'm always impressed when people devote their life to doing something unique, and I always enjoy hearing them talk about it. I think probably what impressed me most about that conference was the wide variety of NMR that was being presented. I'll resist the urge to talk about names because then I'll forget somebody. But I really enjoyed that there was just such a diversity of techniques and applications. And I also enjoyed the conversation. So for me, a meeting is really all about the dialogue. Yes, of course, I love sitting in a chair and watching people show slides and nice pictures and whatever. But really, for me, the interesting part comes when we go off script and start talking about what does this really mean, or how could this be applied to my situation. This to me is where the magic is. This is where things get interesting. And I enjoyed the fact that we had good conversation. There were questions from students who come with a certain degree of naivety by necessity. I don't really understand what you're talking about. Please explain it. That, of course, forces us to make those explanations and think more clearly about, how am I really being perceived here? But also questions from experts who say, well, have you thought about that? And then, well, yes, but maybe not hard enough, right? So this is how advances are made. And so that's the thing that I really found the most valuable and generally find the most valuable. The worst kind of conference is the one where everybody gives up, takes their, computer, and they get up and they take their 15 minutes and then they walk it down and they're so relieved that nobody asked any questions. Well, okay, well, you probably just wasted your time. It's a notch on the CV, but there's nothing more came out of it. Yeah. And so dialogue and discussion is really the greatest gift of these conferences, in-person conferences.
So I have a few questions about science and education. You chair the executive board of a family business, which is
Indeed.
Yeah, it's unrelated to the academic world, scientific world. Yeah, but in a way, these two jobs, they are similar, isn't it? Both you need to have product, the personnel, the financing thing, managing thing. Do you think that having a research group is like managing a business?
Yeah, I just don't have very much money. I often think about the connection between these two. So I'm the vice chair of the board of Kroeker Farms Limited. So it's a family company, and we're a farm. We make potatoes and sell them all across North America. And I've been involved with this quite deeply for a long time. And I sometimes joke that it's my second job because I do put a lot of effort into it and a lot of time, and I care a lot about it. Family company, but it's also a company that I've just come to really love what we're doing there. It's interesting one of the great things about a company is that it can be more nimble than a university can. In a university setting, there's a lot of bureaucracy. There are a lot of structures that keep us in our place. And there's good reason for this, because universities probably shouldn't function as businesses. We need to have these structures. But it does restrict nimbleness. We can't make changes as quickly as we like. So if I want to shift my research area, I can't really do that easily. I have to first write proposals, and I have to, get money and all of this sort of things, find students. And there are so many things that have to happen. In a business, if you decide on Tuesday that you would like to go into a different type of field, or if you'd like to move around, you can do that by Thursday or Friday. Or at least you can start making moves towards it, which can come to fruition quite quickly. Of course, this is a farm, so we do have to go on the seasonal growing cycles, but we can make big decisions in a very short period of time. And of course, money is a big difference as well. I mean, the company's a $180 million business, so I run a much less lucrative business here in my group. The Kroeker Farms has many hundreds of employees, and I've got a small group of 7 or 8 people. So those are big differences.
Yeah. So you are a tough reviewer, aren't you? I heard it.
No, I don't know where you heard that.
Yeah, in a conversation with one of the glass scientists, someone actually mentioned that, he's a Scott Kroeker, he's a tough reviewer. So when you receive an article for reviewing, what's the process for you? How do you actually take a look at it?
Well, first of all, I'm not sure that I'm a tough reviewer. I do think that I'm demanding in the sense that, let me first answer your simple question. The easy question is I always read the paper first without any prejudgment. I just read it. I don't even try to understand it. I just want to get through it and see what's in it. And then I go through again. And I work through it with an eye to understanding the logic. And then I work through it a third time. And on the third time, I come to it with the critical eye. So first time, what's here? Second time, what are they trying to say? And third, where are the holes? Where are the weaknesses? And I often find that at the second stage already, I'm starting to ask questions because the logic may not be very well formed.
Yeah.
At the third stage, I am going to ask those hard questions about the NMR spectroscopy. I review a lot of different types of papers, and most of them have something to do with NMR. And so I often see that my area of expertise, my strength, is to ask the questions of, is the NMR spectroscopy experimentally valid to the best of my ability to understand what they've done? And are the conclusions drawn from it valid? Are there other possible explanations? Have they considered them? And I think that if I'm a tough reviewer, it's because I really want the connection between what the NMR spectrum is telling me and the interpretation and the conclusion to be one piece. And I fear that very often the conclusion is, again, I'm not speaking about a particular paper, but too often I sense that the conclusion was written before the experiments were interpreted. And so the experiments were used to support a conclusion that was already preformed. Well, that's not the right order. It should be the other way around. And sometimes you do an experiment and it comes out exactly as you predicted, and it does support exactly what you expected was going to happen. But in the main, we find things that we don't understand. And when we don't understand them, what do? We ignore them, run the experiment again, start a new project? Or do we look more deeply? And I think it's that looking more deeply that isn't always done.
Okay, that's interesting. Let's do the next part, beyond the lab. Always I would love to know about the personal aspects of that scientist, the researcher. So what do you do at your spare time?
This is my spare time, doing an interview with you. So I like to run. I love to ski, provided we actually get snow. We haven't eliminated our winter, but I love to ski, cross-country skiing. I love to run. I love to cycle. I am very involved in music. I play music and I listen to a lot of music. I care a lot about different types of music. Of course, I have the farm, which takes a lot of my spare time, if you want to call it that. And I have family. And so those are a few things that occupy me when I'm not sitting in this office.
Which instrument do you play?
I play the alto saxophone.
So what was your dream job when you were a kid?
When I was in grade 9, my friend and I made a pact that we would become biochemists.
Close to, not that much close, but
Well,
chemistry.
Well, it doesn't feel close now, but at the time I knew exactly and it was very simple. I wanted to help people, and the way to help people is to become a biochemist. There's some truth in that. There's also it's not quite that simple, obviously, but I just had a very clear sense that I wanted to devote my life. I felt called to doing something in my life that would be helpful to people. And that was the thing that came to me in grade 9. And so I guess I followed that. Although, to be honest, when I got into university, I was very involved in music. I had my own jazz band. I was playing with several bands, and I felt like there was a decision to be made. And there wasn't any way I could do both. I had to make a decision. And I very nearly went into music, but I didn't.
So in an imaginary world, what's your job? If there were another world, a parallel world, if you could pick another job.
It's tempting to say that I would like to do music.
Yeah.
But of course, when one turns one's hobby or one's love into a profession, then it becomes subject to competition, and it becomes subjugated, you might say, to the demands of economics. And so something that one loves, whether it's music or poetry or art or whatever, all of these great things they would do, it becomes very difficult to sustain. And so it can go from being a joy to a burden very quickly. And I think that almost everything that we choose to do for a profession has a tendency to go that direction. And so I think it's too difficult to answer what I would do in an alternate life.
Okay. Do you have any regrets?
Any regrets?
Your career, if you could decide, decide something differently.
Well, let me put it this way. I had a few other opportunities when I was considering this position. I had 2 other opportunities, and I have always wondered what it would have been like to take those. They would have taken me in very different directions professionally, still solid state NMR of classes, but they were very different opportunities. And I won't say that I regret coming here. I don't. But I will say that I've always held a curiosity about what would my life have been like if I had gone there or there.
You know, that's something sometimes I think about. It would be interesting if we could see another path, if we decided to do something differently. So if a time machine existed, you would rather travel 200 years back or forward?
Oh, back. Definitely back.
You love history?
I'm afraid of the future.
Oh, yeah. So for the last question, who is your favorite scientist in the history?
Oh, it's a hard question to answer because I assume you're referring to people that I didn't know personally.
Yeah.
So you're referring to people who somehow became famous enough for me to know about them, which means that these are people who probably make great scientific contributions, but at the same time, they quite likely devoted themselves single-mindedly and wholeheartedly to doing one thing their whole life. And in fact, many of the discoveries or inventions, choose your word, that we have come from people who are quite single-minded and not particularly balanced. And so I don't know who my favorite scientist would be, because probably they didn't become famous enough for me to know about them.
Okay, that was the interesting answer. So thank you so much. Thank you for your time.
My pleasure.
Thanks for your thoughtful insights and comments and answers.
It's my pleasure, my team. And now, Mujtaba, I'd like to introduce you to my other life, my other world, my other job. This is Kroeker Farms, of which I've been a part since before I was born. This farm was started by my great-grandfather in 1928, incorporated in 1955, and it's grown a lot over many, many years, and now we farm a lot of acres, something like 8,000 or 9,000 acres. We do about 1/3 conventional potatoes, about 1/3 organics, and about 1/3 creamers, the small potatoes that show up on your restaurant plate. We have yellows, reds, whites, purples, and we've got a lot of business from our organics. So this is one of the things that we've done a lot of in the past, decade and almost 2 decades now. We've really been focusing on increasing our organic production, and we are now one of the largest organic producers in North America. And we ship all over North America, mostly US and Canada. And we take a lot of pride in the potatoes that we grow. And most recently, we've done a lot of packing and shipping and processing, not processing for processed potatoes, not French fries, not potato chips, but table potatoes, because we make really beautiful potatoes that look good and taste good and are healthy. So healthy food, healthy world.
So I'd like to introduce you to one of our beautiful fields. This is a field of potatoes, which is our beautiful soil. And every time I walk into a field, I want to touch the soil and feel how beautiful it is. And this particular field has some really nice potatoes in it. One we call a beautiful stand, because the plants are starting to come up in a very uniform way. And you can kind of dig in here a little bit. It's a little bit too early to see any real potatoes, but underneath here, we're getting to see the beginnings of these tubers. And eventually, of course, these will give rise to some beautiful potatoes that we will run through our beautiful packing plant, and then you'll eat on your table.
Oh, yeah. Thanks for doing this great job.
Okay, so welcome to our Kimberley wash and packing plant for Kroeker Farms. This is a new construction. It's only been operating for a few months now. And what you see behind me are packing and sorting lines. We harvest our potatoes in September, and we often end up shipping them in July and August. So they have to sit there for almost a year. Those storage spaces are what makes that possible. Mm-hmm. And this is not always possible for every storage, but we've designed them specifically so that we can ship year-round. Sometimes we run out, but for the most part, that's what we like to do. There they come. Here comes the first batch of fresh, clean, dry potatoes. And they're going through a machine to make sure there's no metal and there's no extra stones or anything like that. And here they come. And this is the potato store. And here are our Kroeker Farms red potatoes. Yeah. Here are our organic potatoes, Poplar Grove, another one of our brands. And these are I'm especially proud of these because these are our low-carb potatoes, Adora. And they're a great potato for for baking, for boiling, for frying, for roasting, almost anything you want to do with it. This is a great potato. So Adora, there's our pitch from our sponsor today.